John initially saves and makes a contribution of $5,000 a year at the end of the year for his retirement for 6 years. After 6 years, he's unable to make contributions, but is able to leave the retirement account alone for the next 24 years. If interest rates are 4% compounded annually, how much will John have in the account after 30 years? So there's two pieces to this. The first piece is that he's making contributions for 6 years of $5,000, and they grow at 4% compounded annually. And then after that, he leaves whatever is in the account alone and lets it grow for 24 years. So this part is just straight compounding interest for 24 years. This first part is an ordinary annuity for 6 years with a contribution of $5,000. And so the amount that he has at the end of the 6 years, so the future value of this is the principal to start this compounding growth for the next 24. And at the end of that is what he has in the account after 30 years. Okay, so don't know future value. We're trying to find that. Contributions are $5,000. We have annual compounding. So 1 divided by 1. The number of years is 6, and the interest rate is 4%. So the number of periods is going to be 6 because it's 6 times 1, and again, convert that to a decimal. The period interest rate is going to be 4% because you divide it by 1. Okay, and we need to find what the future value is. So future value is, for an ordinary annuity, is the payment times the growth factor from the geometric series. Okay, and we know interest, number of periods, and the payment amounts. So just plug in. And let's see, so you get 1 plus 0.04, the n minus 1 over 0.04. So 0.04 to the 6th. Make sure that's clear. 6. So 1.26 here. So 1.26, again, keep the decimals, minus 1 over 0.04. And then all that times 5,000. So subtract 1. So 0.26 over 0.04 times 5,000. So 5,000 times 6.63. Okay, so the future value of the annuity is $33,164.88. I'm rounding at this point on that because this is the amount you're going to then use as the deposit. So now for the compounding growth for 24. So our interest rate here is, again, 4%. Our time is 24. Our compounding is still annual, so n is going to be 24 because it's 24 times 1, 0.04, 1. So our period interest is also 0.04. Okay. And so we have annual compounding. This is going to be our principal amount. Again, this was our future value from the prior annuity. So this is going to be the principal, and we're trying to find the new future value for this. So future value is principal times your growth, and then times the number of periods. So you have your period interest and your growth there. So we have our prior result $33,164.88 times 1 plus 0.04 to the 24th. So 1.04 to the 24th times this principal from the prior. So this piece is approximately 2.56, and so you multiply that by the principal end result, the end result from the prior one, and you get 67 cents. Yeah. No, 68. So if you look at the formulas, this one, that what we did here is actually very similar to the present value, or the present value for the deferred annuity, because you have this period where it grows without being touched. But except there, the order is reversed. You deposit the sum, let it grow untouched, and then you start withdrawing it. So it's reversed around. But if you look at the calculation internally, which I'll just quickly put what it would be. So you have this part, and then times this part, which is the growth part. So 1 plus I to the n. Except this would be k here, just to not be confusing. So we're going to use n repeatedly. And then this is r 1 plus I to the n minus 1. And that is 6. So if you check this out, just as an aside, this is similar to the present value form of the deferred annuity.